so now we're on 17.1. This is the last chapter, chapter 17, and we're only doing 3 sections in this last chapter, so really we're almost done. The cool thing about chapter 17 is the fact that almost all of what we're going to do is review of some of the concepts that have come earlier. The only difference is that now we have some theorems that tie together concepts that we've already discussed. So the good thing is it's sort of a review and it's mostly computations that you're familiar with. The bad thing is I'm going to talk a little about theory, which you probably don't like that much. So let's talk about Green's theorem. So Green's theorem is an important theorem that ties together the idea of vector line integrals and double integrals over a plane, which is cool. So learning goal number 1, I'm going to introduce some new notation. Most things I'm pretty excited about. This new notation is something I'm not very excited about, but I'm going to introduce it anyway because it is important to be able to, not all books talk about this the same way, and our book in particular does talk about it this way. So I'll introduce PQ notation for vector line integrals. Then I'll state and apply Green's theorem, and as part of that, we're going to define something called scalar curl. So we're going to start with a quick review of vector line integrals. So recall, this is how we describe a vector line integral. It's going to be a vector, and it's parameterized by some distance. Typically, we parameterize the length of the line by a path given by C of t. Our formula that you should be comfortable with, that you now have on your note card and in your brain, is the fact that a vector line integral is given by f of c of t dotted with c prime of t. And recall, it's going to be a dot product instead of multiplying by the magnitude, because this is a vector and this is a vector, and so we take the dot product of those two vectors. So now I have some new notation for you. It's exactly the same thing. Why do we have this complicated notation? I'm not really sure. I think it has historical origins. However, when talking about Green's theorem, everyone talks about Green's theorem in terms of p's and q's instead of just components of the function. So I'm going to follow suit. We're going to talk about it in terms of p's and q's. So first we have to talk about how do we represent vector line integrals with p's and q's. What is p's and q's? We're going to represent this as the integral of p dx plus q dy, where our vector field f, the first component of our vector field is given by p, and the second component of our vector field is given by q. So previously we had defined these as f1, so f1 is equal to p, and f2 is equal to q, meaning the first function part in here is our p part. Why does this make sense? So let's say our path function is given by c of t is equal to x of t, y of t. And we know this. We know that our first component function is where we are in the x. It's our x coordinate, and our second component is our y coordinate for this path. Let's consider, what is c prime of t? Well, really it's the derivative of this first component with respect to t, right? So really it's the derivative of x of t dt, and the derivative of this y component function, y of t dt. If I omit this t notation, I see that this is really where my dx is coming from, and this is what my dy is coming from. Because when I take this dot product, consider the dot product of f dotted with c prime of t. I can think of this as p comma q dotted with this version of c prime of t, which is dx dt dy dt. And I see that I end up with p dx dt plus q dy dt. And if I plug this chunk into here, I see that my dt's, these differentials, essentially they eliminate one another, and it's because this differential with respect to t is canceling out the fact that we took this differential with respect to t. And so I end up with my p dx and my q dy. This is a little hand wavy, but the idea is that this notation is exactly equivalent to this notation, and in some ways it's a little silly that we decided to have two different notations. You might be wondering about, well, what about these p's and q's? Are these going to be functions of x and y, or should these be functions of t? When you actually compute this, you end up plugging in t's, and so it ends up being exactly the same thing. And that's where I'm going to go next, is with a very brief example. I think that'll illustrate what this notation is doing. So let's say we have some vector valued function given by 3xy, y squared, and a path function given by t, 2t. And let's say that we want to be able to compute the line integral of this vector field over this path, and we're going to do it both these ways. I'm going to do the new way first, and then we can compare it with the traditional way. So if we're thinking about this in terms of our new way, we see that our p is going to be our first component function, 3xy, and our q is going to be our second component function, which is equal to y squared. So if I wanted to write this integral, my path integral in this case over this vector field would be given by 3xy dx plus y squared dy. Just a funny way of writing it. But when I actually want to compute this, I have to go into my t variables. So yeah, this is an integral over c. So when I compute it, I have to do a little scratch work. My dx in this case is the derivative of this x component with respect to t. So in this case, I'm thinking to myself, what is the derivative of this x of t function with respect to t? And it's just going to be 1, because the derivative of t is 1. Similarly, dy is going to be the derivative of 2t, which is just 2. So now I know what dx is equal to and what dy is equal to. Next, I have to evaluate my 3xy at this point c of t. So I'm going to plug in 3 times what is x? X is equal to t. What is y? Y is equal to 2t. And what is dx? Dx in this case is equal to 1. What is y squared? Y squared is 2t squared, 2t all squared, and dy is equal to 2. So I've translated it from this PQ notation to be able to compute this integral. I translate it all in terms of t's. Oh, I didn't give a bound on t. We'll leave it as an indefinite integral, because we aren't actually computing this anyway. So what is this integral equal to? This integral is equal to 6t squared plus 4t squared times 2, which is 8t squared, and 6 plus 8 is 14t squared dt. So I just simplified what each of those terms were. So that's how we can look at this using our PQ notation. If we were to have done it the old school way would have said, I want to look at what is f of c of t, and then I'm going to take the dot product with c prime of t. We'll see that this works out very similarly. The f of c of t in this case, I'm going to plug in my c of t path into my f function, and I got out the vector 3 times t times 2t. Look familiar? And I plug in my 2t for y, and I end up with 2t all squared. And I'm going to take the dot product of that with my c prime of t. And in this case, c prime of t, also looking familiar. The derivative with respect to t is 1. The derivative with respect to 2t is 2. And so it means that my final integral, which is going to be f of c of t dotted with c prime of t, ends up being f of c of t, which here is given by 6t squared, comma, 4t squared, dotted with c prime of t, which is 1, 2 dt. When I multiply this out, I get 6t squared plus 2 times 4t squared is 8t squared, which, like we saw before, is exactly equal to 14t squared dt. So all of this talk was just to introduce this PQ notation.